Good afternoon. I'm Bethany Maddox, and I'm a member of the customer care team at Vitech Corporation. I'm very pleased to be your host for this webinar today as we discuss the world of systems. Before we get started, I'd like to take a moment to review a few technical details. First, we encourage you to ask questions. Please feel free to submit your questions at any time through the Q&A function in the GoToWebinar window. I will be monitoring these throughout today's event, and we plan to respond to questions at the end of the webinar, so please send them in. The webinar is being recorded today. If you're having technical difficulties during the presentation, an online archive with this presentation will be available within 24 hours of the live version. I'd like to take a moment to introduce Zane Scott, our speaker for today's presentation. Zane is the Vice President of Professional Services and Training Organization at Vitech. For the past 30 years, Zane has built a skill set which enables him to provide insight and guidance to individuals and companies as they improve organizational processes and methodologies across their organizations. Zane is the author of numerous white papers, including 9 Laws of Effective Systems Engineering, and is co-author of Vitech's Primer for Model-Based Systems Engineering. Please join me in welcoming our speaker today, Zane Scott.
Good afternoon, and thank you, Bethany, and for the introduction, and thank you for your attendance with us today. I hope that today will be not only educational but some fun. This is a topic that I've had a good deal of fun with already, and one that I hope to develop into several more opportunities to share through webinars. It's a topic that quickly became bigger than I anticipated. I set out a number of months ago to look at the different ways in which we study systems. There are a number of discrete disciplines, if you will, for examining the nature of systems, the design of systems, the function of systems, how systems fit in the world, and these disciplines all approach the issue of systems and systems development a little bit differently, from a little bit different perspective, mostly driven by the constituencies and communities that they serve. And so a while back I began to do some reading and some thinking and to ask questions of my own about how those related to each other, how they were similar and how they were different. And I began to undertake a study of those, and right out of the gate I began to recognize that there's tremendous value not only in the individual perspectives of the different disciplines, but in how those perspectives can integrate together, how they can shine light in each other's areas, and how they work together in terms of understanding systems. I was very, very fortunate to come upon pretty quickly in my research a paper integrating systems science, systems thinking, and systems engineering by Hilary Silito. Hilary is a smart guy who has done a lot of good work over the years in a lot of different areas. But his paper was one that was very, very helpful to me in terms of framing some questions and providing some insight right out of the gate. And I commend that to you. That paper is available, incidentally, through NCOSI, and you can download the PDF if you're an NCOSI member and take a look at it, and I commend that to you heartily. Initially, right out of the gate, I thought that the principal value of looking at these different disciplines was that we could understand that all of the disciplines have different constituencies. The systems engineering community serves a particular constituency centered around mostly defense and aerospace and branching out into some of the more technical areas. Systems dynamics, systems thinking were serving communities that were more process oriented. the business world, the management science world. And so these different constituencies could be united in their interest in understanding and constructing systems, and then we could use the different viewpoints and leverage the disciplines by bringing the different viewpoints into constituencies that were not familiar with them. So you would take a constituency, say the constituency for system science, who are accustomed to studying existing systems like biological systems, and bring the perspectives of a discipline like systems engineering, where we're more concerned with altering, refining, designing, creating kinds of systems. So we could unify the constituencies between the disciplines, and we could leverage the disciplines. That was the real initial promise of the work that I set out to embark on, and I think that promise still holds. It's just that, as you'll see today, I discovered some things right at the gateway that were worth talking about and stopping to examine, and that's what we're going to do today. What were the disciplines that I looked at? I looked at systems theory, and we'll talk about each of these in a little bit of detail so we understand similarities and differences. But I looked at systems theory and then systems science. I looked at systems dynamics and, of course, systems engineering, and then in a more overarching sense, systems thinking. Along the way, I picked up some information and some interest in some areas that are related to this tangentially, that cross over into aspects of this, like axiology. I've actually done a little bit of work with a community. The Hartman Institute is involved in what's known as formal axiology. Axiology is the study of values in systems. Their underlying thesis is that the value of a system is determined by how well it is what it's intended to be. And of course, if you had a systems engineer express that, the systems engineer would say that we judge a system by how well it meets its requirements. So there were areas that crossed over in the field of axiology into the field of systems thinking. The same was true for cybernetics. So these are the basic rocks that I've been turning up to look under. The first consideration, though, when you begin to think about systems, is you look at the way systems are defined. And the NCOSE definition pretty much rings through all of these. They all have three hallmarks in their definition of a system. One way or another, these three things get expressed in the definition of a system in all these disciplines. The NCOSE definition says a system is a construct or collection. Every one of these disciplines has the concept of a whole, that a system is a whole. And then the NCOSE definition points out it's a collection of different elements. And so this whole is composed of parts or elements. And that's your second aspect of all of the definitions. They all have some idea of constituent parts that together produce results not obtainable by the elements alone. So this idea of results that really go beyond what could be put forward by just the parts of the system is a part of the systems definition in all of these disciplines. So the first commonality, the first thread that runs through everything is this 1, 2, 3 idea of a whole composed of parts that produces results that are not obtainable by the parts by themselves. Well, let's look at the different disciplines, talk about them one at a time. The first, and pretty much the first in time, is something called systems theory. This really turns on the work of Bertalanffy, Perspectives on General Systems Theory. This is work that dates to the 40s, 50s, 60s. And systems theory can be thought of as the interdisciplinary study of systems in general, with the goal of elucidating principles that can be applied to all types of systems at all nesting levels and all fields of results. Without breaking that down, what we see there is that the principal character of systems theory is that it's very observational, as opposed to being a discipline where you work on it. So for those of us who are familiar with the systems engineering community, we're always taking an active view. Not only do we observe systems, but we actually work on systems. We try to alter existing systems, or we try to create new systems. Systems theory is more observational than that. The second discipline grows right out of that. The ancestors of systems science come right out of systems theory. And it's seen as an interdisciplinary field that studies the nature of complex systems in nature, society, and science itself. So it particularly focuses on complexity, and it does so in the realm of pure science or hard science. So you're looking at nature, society, and science itself. So it does so at the basic research level. The characteristic that emerges in systems science is an overt focus on relationships. So we're looking at complex systems in systems science, and we're particularly interested in the relationships between the elements in complex systems. From there we have systems thinking, which starts to be an overarching kind of discipline that sort of runs at a high level across all of the different disciplines, and that's the discipline of systems thinking. A process of understanding how things regarded as systems influence one another within a whole. An approach to problem solving by viewing problems as parts of an overall system rather than reacting to specific parts, outcomes, or events, and potentially contributing to further development of unintended consequences. Systems thinking is not one thing, but a set of habits or practices. Here we have a discipline as an orientation. When we begin to get into the world of systems thinking, we start talking about how we approach problems and how we see problems, how we define problems, how we think about problems. And so you can take the principles of systems thinking and make immediate application in these other disciplines, because this becomes a way of solving problems, a way of viewing the problems, as this says, and systems thinking becomes an approach rather than a particular thing. Russell Ackoff is one of those who is one of the preeminent systems thinkers. He comes to this not as a basic scientist, in the sense of a biologist or a chemist or a physicist, and not as an engineer, not as somebody who's dealing with a technological system, but he comes to this out of the business world. And lots of his systems thinking is pointed at thinking about social systems, business systems, process-oriented systems. And so this too is a new perspective that comes into the systems thinking world. He says systems thinking is holistic. It attempts to derive understanding of the parts from the behavior and properties of wholes. rather than deriving the behavior and parts of whole and properties of wholes from those of their parts. So in other words, system thinking turns us around from the way that we think, and we'll talk about how we have traditionally looked at analyzing problems. But systems thinking takes that and turns it backwards and says you can understand the parts in terms of their roles and relationships in a whole, in a system, rather than attempting to understand the system by breaking it into constituent parts. Then we have the discipline of systems dynamics. This emerges from a lot of work done at MIT and several people that we'll mention in just a minute. But systems dynamics, by and large, in our day and age, is a computer-aided approach to policy analysis and design. There are a lot of very good programs, very good tools out there that you can use to engage in the analysis of systems from the perspective of systems dynamics. It applies to dynamic problems arising in complex social, managerial, economic, or ecological systems. Literally any dynamic systems characterized by interdependence, mutual interaction, information feedback, and circular causality. The new distinguishing thing in this discipline is the focus on systems over time, as opposed to looking at systems and saying, hey, what's going on here from the complexity of the numbers of parts? This says, I'd like to take a look at what happens to this system over time, the complexity of the interactions. And it's here that we begin to get a recognition that systems within systems will affect each other. A system operating in an environment will impact the environment, which will in turn impact the system. And so these feedback loops, information feedback, and the interactions and causality is the meat and potatoes of systems dynamics. As I said, this came from the work of a number of people, but probably preeminent among them are Jay Forster and Donella Meadows. Jay Forster at MIT, and Donella Meadows at a couple of different schools, but they did their work and their teaching around the feedback loops, the interactions, and looking at things like stocks and flows. This is a very commonly used example of feedback loops where births add to a population, and the more people you have in a population, of course, the more opportunities there are for matings and additional births, which then add to the population. Then you have a loop running in the other direction where the more people in the population, everybody in the population is going to die, so the more people you have, the more deaths you have, and deaths subtract from the population. So you have these interactive feedback loops. That's systems dynamics at its very simplest level, and that's what came out of their work. There's an emphasis here in systems dynamics on patterns. You want to look beyond any individual element and ask how that element fits in an underlying pattern. This makes it particularly useful as a discipline for analyzing policy. You look at the policy structure, as this calls out, underlying individual policy decisions rather than looking at a particular decision. So, for instance, if you're looking at political decision making, you would ask yourself, where does this fit in the flow? What are the decisions behind this? If you're looking at historical research on policy decisions, you would say, you know, what comes before this and what comes after this? Where does it fit? in that underlying flow. So events and decisions are seen as surface phenomena, and they're seen as riding on the underlying tide of system structure and behavior. So more important than understanding the events and the decisions themselves is understanding that underlying tide, as this calls it. Then we have a discipline. Most of us are probably from the systems engineering community, so we won't have to belabor this discipline at any great length, but let's look at it to see what makes it different. The NCOSE definition of systems engineering says that this discipline is responsible for creating and executing an interdisciplinary process. And that process has the purpose of ensuring that the customer and stakeholders' needs are satisfied in a high-quality, trustworthy, cost-efficient, and schedule-compliant manner throughout the system's entire life cycle. In other words, the whole focus of the systems engineering discipline is not to observe the system, although we do some observational work, but to influence it, to change it, to design it in the first place, to change it over time, to impact it at every point in the system life cycle. So this discipline is intentionally interventional, and it's a discipline where the focus is on the activity of interacting ourselves with the system or the system design. So as I began to do research and begin to look at those systems, it struck me that there was a very important idea right here at the threshold, right as I opened the door to doing this work. There was an idea, and that idea was the idea of systems itself. Looking at that idea from the different perspectives. Now, what do I mean here? Well, let's back up a little bit. The Enlightenment brought on a scientific method and taught us that the way we understand a whole is by breaking it down and understanding its constituent parts. So the primary tool of enlightenment was analysis. You take something apart in order to understand it. One of my brothers is a very analytic person. From the time we were just little, he wouldn't take a toy. If you gave him a toy, he wouldn't just take it and play with it. It would not be long until he took it apart. He would experiment with different ways of reassembling it. But he was analysis personified. He had to break everything down into parts. In fact, we went through a time somewhere late in elementary school where it was a race to get to the house so that he couldn't disassemble all three of our bicycles and reassemble them in some way that was most advantageous to whichever result he owned when the reassembly was over. But he wanted to understand things, and he got his understanding by taking things apart and looking at the parts. Now, the systems perspective calls for a new way of thinking. If you read Russell Ackoff or you watch him on YouTube, and I recommend anybody who's interested in this area of systems thinking, go to YouTube and watch Russell Ackoff videos. He's a very colorful character. If you're sensitive about language, you may want to be careful as you watch him to not watch him with small children, because he is so colorful in his language. But he's colorful in his illustrations. His way of thinking is very fresh. And he says that we have to adopt a new way of thinking, that we need to think synthetically and not analytically. In other words, he says we can't best understand the whole by tearing it down into its parts. We need to think about the whole as the whole. And what he means here is, if we go back to the definition of system, And we see that a system is a collection of parts, a collection of elements that operate together in a way that yields results that are not possible through the operation of the individual parts. We'll see that if we break apart the relationship between the parts, if we disassemble the system and look at the parts individually, the piece that we lose is the very essence of the system. And that is through those relationships, through the synergy that's created by the elements as they relate together, then we lose the essence of the system. So he says we need to preserve the essence of the system as we study it and think about it in synthetic and not analytic ways. So this involves a new paradigm, a new systems paradigm. You can see this in the work of people like Capra, who is he's trained as a physicist, but has done a lot of work in the area of ecological sustainability. His thesis is that if we want to know how to operate in sustainable ways in the world, that we need to look to nature to understand how nature operates sustainably. So Capra posits that nature left alone will sustain itself. It'll operate in sustainable ways. So we need to understand those natural systems in order to understand how we might interact in those systems in a way that is sustainable. And out of Capra's work, you have a couple of different principles. He says we need to shift our thinking away from parts to the whole. So he agrees here with Akoff wholeheartedly. We need to shift away from the parts to the whole. And then he says we need to shift from the structures to the processes. That we need to worry not so much about the structures that implement the behavior, but we need to worry about the behavior or the function itself. And here I'm speaking to a systems engineering community, so I'm borrowing systems engineering terms. But where we would perhaps put a lot of emphasis on the physical architecture, he says that the key is to do our primary thinking around the functional behavior, around the functional analysis of the system. He points out that in systems, the properties emerge from the relationships. So if you break the relationships, you lose the properties. You can't really observe a system if you begin to think of it in terms of the constituent parts. You can't really develop an understanding because the essence of the system rides not in the individual parts, but in their relationships together, in the whole of the system. This is not really a new idea. This is an ancient Sufi wisdom saying. You think because you understand one, you must understand two, because 1 and 1 makes 2. But you forget you must also understand and. So in other words, just because we understand the two individual elements that make up the two parts that make up the sum, we need to also understand the operator in the language of math. We need to understand the concept of and. So 1 and 1 does make 2, and we understand 1 and we understand 2. But we also need to understand the relationship there. So where does that take us? Where can we go from understanding that we need a new paradigm? How does that impact us on a practical level? Well, I think it takes us to a new understanding of two of the biggest challenges we face. We face the challenge of increasing complexity. things get more and more complex every day. And in the systems engineering community, we have to deal with that. The problems are more complex. The potential solutions are more complex. The interactions are more complex. So we're having to wrangle complexity at every turn. And the second thing is that one of the keys to wrangling that complexity is to foster innovation. So two of our biggest challenges in the systems engineering community are wrangling complexity and fostering innovation. And this new paradigm gives us some new insight into both of those. Let's talk first about complexity. First, there are two kinds of complexity. If you want to see a good discussion of this, Peter Senge talks about it in the book, The Fifth Discipline. You have detail complexity. If I say complexity to somebody on the street, if we were going to go out and do jaywalking like Jay Leno does and ask, what is complexity? Most of the answers would have to do with detail complexity. So an increase in complexity means going from the direct drive of the sprocket change on the bicycle that we had at kids to the deraillers and all of the complexities that give us 10 gears, 10 speeds, 20 speeds, 21 speeds. All of that, the addition of those elements and the ways that they're put together is what we call detail complexity. But we also have dynamic complexity, and dynamic complexity is what systems dynamics focuses on, which is that over time these elements and systems and subsystems are all going to interact in ways that will alter their environments and actually alter them in response to the environments. So we have a complexity in details in the structures, and then we have a complexity across time, detail complexity and dynamic complexity. Then we can look at how we've dealt with that complexity in order to understand kind of where our understanding of the problems has gone. Before the 19th century, the primary way that we dealt with problems was try to break them down and make them as simple as possible. So we dealt with the problems as simplistic issues of causation. So we tried to break down any kind of a causation study, for instance, into a set of equations that says A causes B and D causes E, and so we would break it down into a whole series of simplistic problems. Then we began to realize, as science advanced, especially in the 19th century, we saw that there was complexity out there that didn't get very well explained by these systems of equations and linear ideas of causation. And so we begin to say, well, we think that's probably from disorganized complexity. Things are not so neatly organized, and we were having trouble bridging the relationships between things and seeing the complexity as simply bewildering. As the 19th century ended and the 20th century began, we began to recognize that what we thought was disorganized was really organized, but organized at levels beyond and organized in ways beyond what we had previously understood. So we were dealing not with disorganization, but with an organized complexity that we could, by gaining a better perspective, come to understand. What's that perspective? That perspective is to try to get sufficient elevation in our thinking to be able to take a systems view that encompasses all of what we need to be thinking about. So we begin with simple linear kinds of causation formula to understand the world around us and how things work. Then we saw the disorganization, what appeared to be disorganization around us, and tried to explain it. And now we are coming, as with the fractals here that are produced with mathematical equations, to recognize that there are driving organizations and systems and ways of explaining it. And we begin to try to gain sufficient perspective to do that. Just as an illustration, on the left here you see an Aristotelian tree. This is an explanation of knowledge from the Aristotelian viewpoint. So you have a substance, you ask first, is it material or immaterial? If it's immaterial, then that substance is spirit in this ontology. If it's material, then it has some sort of a body. Is it animate or inanimate? If it's animate, it's living. Is it sensitive or insensitive? If it's sensitive, it's an animal. In this system, is it rational or irrational? If it's rational, it's human. And then you have specific examples. So the Aristotelians would take knowledge and plug it into this tree structure. And we use the tree structure over and over again in numerous examples as a way of building ontologies, categories that break down and branch. And so we use the tree ontology. Actually, to see this as a tree, you'd need to turn it upside down. And it would look more like a tree. This looks more like a root system this way. The drawing on the right actually is a map of Wikipedia. This is a map of the knowledge in Wikipedia, drawn by Mark Nozell. This is much more complex, as you can see, and it doesn't really operate as a tree kind of an ontology. It's a different clustering and a different organization, and it represents the complexity both that existed always in the knowledge, but secondly a complexity that now exists in our understanding of how that knowledge is organized. So we're dealing with an ever-increasing level of complexity. How do we do that? What are the implications here? The implications here are that we need to raise our thinking up to a systems perspective. In other words, we need to be able to see the whole of what it is that we're dealing with. We need to be able to appreciate detailed complexity and dynamic complexity. When we teach model-based systems engineering, we, at one point in the course, always say there are three basic systems in any systems engineering project. One is the system, and in a lot of these systems disciplines, it's called the system of interest. The system you're working on, the system you're designing. In this case, a subway train. So we have a subway train, which is the system that we're focused on. But this system we're designing here is going to go live in a larger system that we call the environmental system, the environment that it lives in. So in this case, the subway train's going to go and live in DC Metro. That happens to be a DC Metro map there. And it's going to live and operate in that environment. And then we have a system that often we don't do much thinking about, which is the system that we use to design or change or manage the system of interest, our system. Well, if we're going to deal with the detail complexity of doing the design and understanding the environmental system and the dynamic complexity, in other words, when we introduce this new train that we're designing into the environmental system, it's going to interact with it. And over time, the design and maintenance system that we use to design and maintain this subway train will interact with it, and it will alter the design system to meet the needs of the design and maintenance and the system of interest will interact and alter the environment. The environmental system will interact and alter that. That's all dynamic complexity. How in the world can we deal with the detailed complexity and the dynamic complexity? And incidentally, James Martin has a very interesting paper out there that he calls the Seven Samurai of Systems Engineering. And he talks about these different systems and how they alter each other. And he, instead of 3, he uses the example of 7 because he takes into account the dynamic complexity over time, the ways that these systems alter each other. But how in the world can we get a grasp on that? Well, I think the linchpin here is the systems view. I think that's what gives us the real ability to get up to a systems level where we can hold within our contemplation of the problem and the possible solutions the entire systems that we're dealing with. Now we have problems that result from not doing this. If we don't get that high, if we don't get high enough to understand not just the system of interest but the environmental system, we can have all kinds of unintended consequences. In this particular example, we're dealing with the need of the fur trade to produce high-quality fur very quickly. So we need a fur-bearing animal that has a high-quality fur that's very prolific. In other words, it produces young at a very quick rate that can mature and produce this fur. We would prefer that it eat almost anything so that we can feed it cheaply, that it be climate resistant so it can live anywhere we want to propagate it, and we want it to be disease and predator resistant, have very few predators, and be disease resistant so that it will be very survivable. So in response to that, if you were to read this ad in detail, you would find that they're advertising rather, that this animal that they located in South America called the nutria meets all of the requirements of solving that particular problem. Basically what you have here is a rat about the size of a small dog. So this rat meets all of these criteria. And so they brought the nutria from South America, imported it into Louisiana, East Texas area, and began setting it up in fur farms. Well, the problem is it has 20 young a year, so every female, if you had 20 females, the next thing you know, you have 400 nutria. And then the 400 expands. It's very prolific. It's disease resistant. It'll eat almost anything. It can be fed cheaply, so it's not long till it breaks containment. Well, when it breaks containment, there aren't any limitations on where it'll go because it's hardy, it's disease resistant, it doesn't have many natural predators, and it can live in any environment. So here we are 60, 70, 80 years later. I'm not sure exactly when it was first imported, but this picture down here in the lower right corner is a picture taken in a marshland on the eastern shore in Maryland. And it's damage from these nutria who have spread that far. These are unintended consequences unleashed in the environment because we weren't thinking about the environmental system when we, quote, solved, unquote, the particular problem of the fur-bearing animal that we needed to make a profit. And so now the need and the appropriateness of the fur-bearing animals has long since kind of faded away, and the economic justification for having them is gone, and we're stuck with the downside consequences. So the failure to adopt this system view can have all sorts of far-reaching consequences. The other way that taking the systems view helps us is in the area of fostering innovation. Poincaré, the French mathematician, said, "To create consists of making new combinations. The most fertile will often be those formed of elements drawn from domains which are far apart." In other words, if you're going to be creative, one of the things that you have to learn to do is to create solutions that span across the conventional ways of thinking. Gutenberg's printing press revolutionized the whole area of knowledge management, which opened the door for all sorts of innovations. When people point to the major innovations in the course of civilization, this one is a seminal innovation. And Gutenberg does it by expanding his thinking to include a wide variety of things. He looks to the wine industry, to metallurgy, to chemistry, to business organization in order to make his innovation. How does he do that? Well, when you look at the Gutenberg press, you see that he adopted a technique for the press from the wine industry. So he has the screw mechanism with the handle that he uses to apply pressure to the plates and to make the prints. To that idea, he adds the idea of movable type. No longer would it be necessary to etch out the entire plate that was being printed, but you could simply set the type and make the print from type that had been set and locked into place. One of the problems with the movable type was it becomes possible to turn individual letters upside down or have things come out backwards. So Gutenberg introduces another innovation, which is that he makes a non-printing aligning mark on each one of the pieces of type. So you can then visually scan a page of type that's been set, and the presence of these alignment marks will tell you whether or not things are all lined up as they should be. He looks to the world of chemistry to produce a better ink that makes a better image and lasts longer and is more economical to use, so he introduces better inks. He looks to metallurgy to come up with metals that can be easily cast into type, and the type will be more durable and will last longer. Of course, you're mashing down on this type that has a raised typeface on it, and so he makes it more durable and more easily cast, remelted, and cast again when necessary. And then finally, instead of having one single printer who's doing this entire job of inking and operating the press and putting the paper in and handling all these operations as a one-person operation, he sets up a division of labor and sets up the first press crews. So he's able to make this innovation by drawing on all these different areas: the wine press, the ink technology, the metallurgy, and the typesetting, and the division of labor, to come up with this innovation that makes the printing press, which allows the mass production of books and other printed items for the very first time. So his innovation is one that spans across disciplines and across bodies of knowledge. To see another example of this, all we have to do is look at the vacuum cleaner. The vacuum cleaner's basic design is you have a dust collector that's on the floor. You have a blower of some type that pulls air that's been stirred up by the dust collector on the floor that hopefully contains the dirt that was on the floor, pulls this air up into the vacuum cleaner and into the bag, and the bag acts as a filter that traps the dirt, and then the air is exhausted out of the vacuum cleaner. That's the basic vacuum cleaner design. Now, over the years, people tried improving this, and the typical way that they would improve it would be to go after one of these parts, one of the parts of this system. So you develop a better blower that, for a given level of power that's available, produces a stronger suction, a stronger flow of air. Or you introduce little electric motors in the agitator so that your vacuum cleaner has little brushes that whirl around in response to an electric motor that drives them to stir up more of the dust and pull it in. And people worked on the bag design, designing the bag as a membrane to increase the efficiency for trapping the dust and yet allow air to pass through it, because over time, as the bag began to fill, it would essentially stop off the flow of air and therefore reduce the suction down on the floor. So all of these were attempted as individual innovations over time. And then along came Mr. Dyson. And Mr. Dyson had an idea that was based on this thing on the right, which is the air exhaust system for a sawmill or a wood shop. And what this air exhaust system does is it takes the air, which is laden with sawdust. If you've ever been around a wood shop, or especially around a sawmill, the air is just full of minute wood particles, this sawdust. And so this thing sucks them inside, and what it does is it causes the air to revolve in a cyclone inside the machine. And as the air revolves, centrifugal force pulls the wood particles out of the revolving column of air and throws them against the side, and then they slide down the side, and you can see this is conically shaped so that they slide down and actually drop into the barrel, to the waste receptacle at the bottom. So you're essentially centrifuging the dust particles out of the air. So Dyson went to the vacuum cleaner and said, hey, let's do that. Instead of a stronger blower, instead of a better agitator on the floor, instead of a better membrane, let's create a cyclone inside the vacuum cleaner. And he made a huge innovation. How does he do it? He did it by looking at the vacuum cleaner as a whole rather than trying to improve one of the individual parts. So he made a systems innovation by being a systems thinker. And of course, since then, vacuum cleaners have evolved to the point where my mom has a strange little thing that wanders the house at night or while she's gone, just a circular disc bouncing off the walls that does this job. But Dyson's innovation had to do with thinking about the system in a whole different way. So what does all this mean for us as systems engineers, or people who operate in the systems engineering community? Well, the first thing it means is that we need to work on our perspective problems. We have perspective problems that keep us from adopting this new way of thinking. We tend to reduce things to specialties. We want to break it apart, and we even apply that to our own profession, to our own discipline. So you'll hear people who will say, I'm a requirements engineer. I just work with requirements. Or how can I verify my requirements without all that behavior stuff? You know, I don't need to do this functional analysis. I just need to verify my requirements. Or I begin my engineering with components. Or I allocate requirements to components. I don't fool with that behavior stuff. All of that, to say nothing of the internal validity or lack thereof of any of those statements, reflects a focus on the components of our discipline, on the individual parts of the discipline, as opposed to looking at the discipline as a whole and adopting a systems view. We wind up getting perspective problems. We adopt tools that only work in one domain of the discipline. We think about the discipline in only one domain or two domains. We drive ourselves down into stovepipes, into individual holes in the system, all of this operates to keep us from adopting a new paradigm, to keep us from adopting a systems view, because we're even looking at our own discipline from an analytical or a component viewpoint rather than taking a systems view, much less taking a systems view of the problem or a systems view of the solution. The systems view as a perspective, on the other hand, allows us to deal with complexity. We can deal with complexity in all three of the systems. We can foster innovation. We can learn to think literally outside the box. We can learn to think outside the stovepipes. We can learn to think about a broad perspective. So it's not so much how much specialized knowledge we as systems engineers have of a particular domain as it is how much domain knowledge can we spread across a great number of domains to draw on thinking. We minimize our risk and our unintended consequences when we do this because we avoid the stovepiping that will lead us to unintended consequences. We avoid narrowing the thinking down. We learn to think from a systems perspective with our own disciplines. We learn to think with a systems perspective with respect to the domains of the problems we face. And we learn to think in a systems perspective about the people, especially those people who call themselves systems engineers. Because if we're systems engineers, we simply cannot afford to categorize ourselves or categorize our work or limit our vision to particular domains and particular stovepipes. Because when we do, we're throwing away our ability to deal with complexity. We're throwing away our ability to innovate beyond a certain point. We can certainly deal with some complexity and we can innovate within the narrowed scope of the vision, but it's an opportunity cost as much as anything else in those two areas. And then we bring on a real cost in terms of risk and unintended consequences. As I say, my work here is ongoing. I continue to look at these disciplines. I continue to believe that these disciplines have things to offer each other, and that it's a fruitful endeavor for us to think about how we might draw on those and draw them together and learn to think in ways that are encouraged within one discipline with another. So I will continue to work and will continue to talk in terms of how we might do that. But understanding that we need to think about our discipline, if that's systems engineering or if that's any one of these other disciplines, we need to think about it as a part of this integrated whole. So kind of the ultimate systems thinking that needs to go on here is that we need to learn to see ourselves as a part of the system of thinking about systems. Here's a partial reading list. This is also a test. If you read these 4 books and then you say, what do these have to do with each other, then you need to reread and rethink. Because if we take a systems view here, then we will look at these books. These are some of the best books that I've read, some of the most helpful. Some I had read before and have since reread in a new light. But Solving Tough Problems by Adam Kahane has to do with the development of scenario planning and the thinking that goes around that. Very, very helpful, very practical book. The Opposable Mind by Roger Martin, likewise, is a wonderful book, and a book that, if you let it soak in, will change your way of thinking. I know it did mine. The Fifth Discipline has been around a while. I've read it all the way through about 3 times, and I consult it often. There are some field books that go with this. One's called The Dance of Change, and I think the other one is called The Fifth Discipline Field Book. But this is excellent work. And then Redesigning Society. If you want to see how this can be applicable totally outside of the realm of technology, how it's applicable in a totally process, public policy, legal world, if you will, read Redesigning Society by Akoff and Roven. It's also a book that will have an impact on your thinking. Well, I appreciate your having spent your time with me this afternoon. If I've infected you with a little enthusiasm, with the desire to read any of these books that you haven't read, with a desire to think about this further or to dialogue with me, then I've been successful. It's not so much trying to show you answers as trying to show you places that you might go to get answers. And so if you share any of my enthusiasm for that, then I will feel successful in this. And I'd be happy to take any questions that anybody has.
Thank you, Zane. Let's go ahead and move on to questions. We've already received a few great questions, so thanks to everyone who submitted those. I encourage everyone to join the discussion and submit your questions at any time via the Q&A function in the GoToWebinar window. Let's get started. Our first question is from Dan. And Dan asks, how do you think a practical discipline like systems engineering can play in the more abstract areas such as systems science?
Thank you, Dan. That's an area where I think there is lots of opportunity. The systems science area, for instance, is looking at, observationally looking at very complex systems. And for instance, the work in this area in biology, in ecology, is attempting to understand those complex systems. And really the next step is a step for systems engineering. It's answering very practical questions like, okay, so now I understand a little bit about the complexity of the ecological system. How can I live in this world in a way that's sustainable? So I think there are questions in there that are calling out for intervention by folks who do have a grasp on how you would design, improve, and maintain systems that are intentionally put there as opposed to systems that are a part of the environment.
Thanks, Zane. Our next question is from Jose, and he asks, is emergence a property of any system? And when do I know I have to consider emergence?
Emergence most often is going to be, unless you have a very, very truncated life cycle, emergence is going to be a property of the system. Sometimes emergence is due to the fact that we didn't gain an adequate understanding on the front end. So sometimes when you see a discussion of emergence, what people are really talking about are unintended consequences. But the other thing that happens with emergence is that in many instances it can be predictable. As particular parts of the system begin to interact with each other, then that's going to create new conditions, and the new conditions then will alter the environment and alter actually the systems that are at work within it. So one of the things, the good things that's going on in the systems engineering world is the stress on interacting with systems across the entire life cycle. So it's not like we design a system as a fire and forget missile and then we let the system go out there. We interact with the system across its life cycle. So we can begin to see the emergence. And when do we intervene in the emergence? Basically, that's going to be judged on when we need to intervene based on how well the system is meeting its requirements and how sustainable it is and how quickly it's moving through its life cycle as opposed to how quickly we would like it to.
Great. Our next question is from Eric, who asks, what one thing would you have systems engineers do or stop doing to leverage what you were talking about here?
I guess if I could have systems engineers do anything at all in order to leverage what I've talked about here, it would be to stop and think about the ways in which we really need to engage in systems thinking. What is it that we need to be doing that makes us truly systems thinkers? We endorse systems thinking. We talk about ourselves as systems engineers, and then we go out and say silly things like, you know, I don't fool with behavior, I just do requirements. Well, that's a very, very limited perspective. Not to take away anything from people who work with requirements, and we certainly do need to work with requirements. But at the systems engineering level, systems engineers need to be able to have that systems perspective. So if you were going to do any one thing, it would be to genuinely adopt a systems thinking mentality. If you want to back that up, then I would go out there and do some reading and some watching and some research in some of these other systems disciplines, because it's amazing what's going on, and things that are our strengths are their weaknesses, and things that are their strengths are our weaknesses. So there's a lot to be learned in adopting that systems thinking.
Okay, our next question is from Raj, who asks, you said not to worry about structure in favor of behavior, but behaviors are dependent on the structure. Can you go into this a little bit?
Actually, I don't think I said don't worry about structure. I said focus on behaviors rather than structures. Let function dictate form. Now, form is going to impact function. That's very true. But the overriding question is the question of function for a system. And to the extent that form is defining function, then we're in trouble. They interact, and you need to be aware of that, and certainly you can't just adopt any old form, but you need to try to make your form the servant of your functions.
Wonderful. Our next question is from Andy, who asks, what one source has been most helpful to you in learning how to think systems?
I don't think that I would, well, my answer would be the 4 books that I recommended have probably had the biggest impact on me. A number of years ago, when I first read The Fifth Discipline, it changed the way that I thought about things. Each one of those books has changed me in some pretty profound ways. And if I were to add a 4th book to that, it would be Donella Meadows' primer on systems dynamics. That would be an addition. But by way of answering what one thing, I would say those 3 things or 4 things.
Thanks, Zane. We have a question from Andrew, who asks, when working with customers or managers with a viewpoint focused on physical architecture or components, how should one go about convincing them to consider a more holistic approach?
Well, I think one of the best ways to do that is to explore unintended consequences. Managers especially understand unintended consequences, and there are numbers of good examples. There are a number of good examples of those things in the 4 references that I gave you. It can be very difficult for people who are, and I don't mean to be really disparaging here, but I suppose that I am being, people with a component engineering mentality have a very difficult time in seeing this. And I think we just have to simply over and over and over again say, you know, here are the downside consequences of focusing so much on physical architecture before you've satisfied the rest of this. The other thing is encourage them to participate in a good overarching course. One of the things that we've done here at Vitech is to try to teach as many times as we can on a half-day basis, on a one-day basis, to teach an integrated systems engineering, and of course we teach model-based systems engineering as an application of it. But really I have seen folks who were pretty much focused on physical structures exposed to that in a systematic high-level way, and I've seen the light bulb come on and they say, aha, yeah, I understand. So you've put your finger on a difficult problem, but one that I think we need to consistently return to over and over and over again.
Thanks, Zane. Our next question is from Jim, who asks, how do we translate systems into doable, trackable actions? Is it driven by a tool or set of tools?
In terms of the nuts and bolts of the design of systems, yes, it would be. And I think one of the things that we need to do is we need to recognize that as we choose tools and choose methodologies, that we choose in ways that will allow us to transcend being stuck in a domain. So if we choose a tool that by its very nature thinks in a stovepiped or domain manner, then we're essentially shooting ourselves in the foot, because all the work done in a domain-oriented tool then has to be picked up, translated, and moved into the other domains. So, you know, of course, our recommendation would be that you have a tool that maintains a model across all of the domains, and that the work you do in any one area is reflected in real time across all of the domains and across the entirety of your model.
Zane, the answer to that question is a really good lead into a question from Willie, and he asks, in dealing with MBSE, how might we address the different levels of abstraction needed to create a model or integrated models that deal with our system functions and behaviors effectively across its entire life cycle?
Well, what we have found over a number of years, beginning back in the days that Jim Long and some others began to get a real grip on this, was that you do need to begin at a very high level of distraction, or high level of abstraction, not distraction. You need to look at the system at a very, very abstract level and begin to close your choices in terms of design and response to your problem so that you converge on a solution. And we do that in layers. So we add detail, we add the detail complexity and the understanding of the dynamic complexity in layers. In other words, you don't try to say, okay, here's the problem definition and here's a solution definition. Let me try and see if that solution solves this problem. You begin with the problem definition and you refine that in layers, and you refine the solution in layers, and you increase the granularity as you go. We call that process strata, and teach that in our model-based systems engineering courses. And of course we teach how to use that with our tools.
Thank you so much, Zane. These questions are doing a great job of leading into each other. The next one is from John, and he says that in the traditional SE process, the sequence has been requirements, functions, then elements. And are you saying that the sequence should be functions, requirements, elements, or should we think concurrently about all three rather than sequentially?
At any given level, and I'll go so far as to add the fourth domain, which is verification and validation, to this. But at any given level, you will think about all four of those domains at that level of detail. So we begin at a very high level, and we think about requirements. Typically you would, if you're designing a new system, your point of entry is probably going to be the requirements that drive the necessity of the design. You know, why do you want a new system? What problem are you addressing? The definition of the problem and the beginning of the very, very high level requirements. If you come from the process world, like I do, most often you're not redesigning the process. In other words, there are very few business organizations who can afford to say, okay, we'll just quit doing the work of this department and we'll let you guys design a whole new process, a whole new workflow for us, and then we'll restart our work. What they want us to do is to come in and improve the existing process in place. So we work in situ. Well, when you do that, yes, your entry point typically is the behavior, because you go in and first define the existing process, and you do that not by defining requirements, but you define the existing process, and then you say, okay, now that we have a model of the existing process, what would you like to be different and why? And you get into the requirements phase, and then you talk about a high-level implementation, and then you start to advance it. But you're advancing all 4 domains from level to level. As you go through the layers, you move from layer to layer in all 4 domains. So you advance your design on all 4 fronts, rather than attempting to take the requirements and drive them to ground, and then take the behavior and drive it to ground, and then take the physical architecture and drive it all the way down. When you do it that way, the traditional model, what was found was that you ate yourself alive in terms of rework. And so that kind of sequential model really it's had some success, but that success is mostly limited to tightly defined, very small type projects. If you get a big project, a complex project, then you need to attack it with the increasing granularity in layers.
Thank you, Zane. We're going to go ahead and wrap up the Q&A for today. There were 2 more questions, one from John and one from Richard, and Zane will answer those on our forum. So you can find that at community.vitechcorp.com. If you think of a question you didn't send in, you can also post that in our forum. And you can also keep up with us and what's new at Vitech by following us on Twitter at VitechCorp. A recording of today's webinar will be posted to our website, vitechcorp.com, by the close of business tomorrow. In closing, I'd like to thank our presenter today, and I'd especially like to thank all of you for joining us. As we bring this webinar to a close, a survey will open on your screen, either in a new tab or in a new window. Please take a moment to provide us with feedback on today's presentation and what topics you'd like to see covered in future webinars. Thank you for joining us, and have a great day.
Thank you.